It's just a science project.
Silent breed is people!
You know, a doctor friend once said the same thing to me. Frankenstein was his name.
It's alive! It's alive! It's alive!
That sounds like something out of science fiction.
Please explain to me the scientific nature of the whammy.
We live in a spaceship, dear.
So? Yes, science!
Program complete. Enter when ready.
Hello and welcome to episode 199 of Science on Top. Today is Sunday the 30th of August 2015. I'm your host Ed Brown, and joining me today is Dr. Shane Joseph.
Hi.
Lucas Randall.
Hey Ed.
And welcome back Penny Dumsday.
Hi Ed.
It's been a while. Where have you been hiding?
I've just had my second baby, so oh my god.
So you are full of energy and excitement and... No.
Yeah. I've been finding it tough, but we're getting there now.
Oh, we are delighted to have you back. We've missed you a lot.
I've missed you guys too.
Group hug.
Aww.
I don't do emotion on this, so no.
You don't do emotion full stop, except rage.
Yeah, except rage. I missed you too, Ben.
Thanks, Shane.
Okay, Lucas, let's start off talking about a bit of a mystery about how our particular solar system got into its current configuration. There are theories that the larger planets formed close to the Sun and then migrated outwards. And now a new theory from David Nisvorny, an astronomer in Boulder, Colorado, proposes that there was a fifth giant planet early on that knocked Neptune's orbit a little and something along those lines, yeah?
Yeah, pretty much. Yeah, okay. Shall we just skip to the next story then?
Fill in the blanks.
It is actually a pretty cool story. If there's one thing we're really good at, and really out of emphasis, is that we're very good at calculating orbital mechanics. Very, very good, because they're based in very well-founded physics. So if you know where things are for at a few different points in time, you can basically trace their route out going forward or backwards. So there's many apps, for example, that make example of this, allow you to fast forward the solar system 20 years and find out where certain objects in our solar system will be, and they'll show you where they'll be. Or you can go back to a certain day in time. Like people have used it to, for example, say, well, what was the position of the planets, for example, when supposedly Jesus was born, for example, and chase it back and say, oh, this was here and that was there, and isn't that wonderful? Now, using those well-established physics, it's possible to build models which will help you wind the clock forward or back and look at some other mysteries in our solar system. One such mystery for a very, very long time is a cluster of these icy rocks. There's about 1,000 or so that we know of, these icy rocks. They're called collectively the kernel. And these rocks hang out in
the kernel does fried chicken.
Wrong kernel.
Someone had to make that joke, didn't they?
K-E-R-N-E-L, kernel.
Right.
Colonel, not as in... yeah,
Kernel as in corn.
Yeah, that's right. So this kernel hangs out in the Kuiper Belt, and it hangs out in a cluster. They're sort of all together. Now, there's been a lot of theories over the years as to what could have caused this little cluster of rock, icy bodies to hang out together. Most things in the Kuiper Belt that developed, together are just in a massive sphere around the sun. They're not on any particular plane. Unlike the planets are all on the plane of the ecliptic. They're all in a very, if you imagine a plate with the sun at its center, the planets all more or less are on that plate. And this is part of the reason why Pluto, was on shaky ground with its claim to being a planet, and part of the reason why it got taken off the table, because it wasn't on the plane of the ecliptic. It was on an eccentric orbit that was quite, on an angle to the plane of the ecliptic. All of the other planets are on the same plane, and if you trace that back in time, that plane around the sun is the accretion disk that would have been around the very newly formed star, our sun, as all of the material that was in our solar system coalesced to one point, caused the star to suddenly have enough mass to start its nuclear burning, and then when that happened, it would have blown a whole lot of material away from the star, but there would have been this plate, this plane of material orbiting the star. Over time, different concentrations of that material around the star formed into the planets, and there's still a really good example of what the pre-formation would have been like with the asteroid belt, where we see a lot of spread out material in a ring around the sun in between Mars and Jupiter, which is the asteroid belt. There's not enough material there to form a full planet. Now, what's weird about this kernel is it's not in a ring. It's in a cluster, it's in a group that are all together. If it had been something like the asteroid belt that just formed a bit further out, it would be in a ring, like the asteroid belt is. If it had formed in the Kuiper belt, it would be a part of that spherical distribution of bodies that are the Kuiper belt. So
where is it? If it's not in the Kuiper belt, this cluster is between Neptune and the Kuiper belt, is it, or is it?
Oh no, well it's now in the Kuiper belt, but if it formed there, it would be in a sphere.
So it's migrated at some point into the Kuiper belt.
That's exactly the point.
Gotcha.
So the theory is that this is a cluster that had formed much closer to the sun, and for some reason or other had migrated outwards. Now things do move around in orbits. It takes a fair while for a system to settle down into a stable system. So if you look at, for example, Jupiter, look at Jupiter with its moons. Jupiter's moons have fallen into, over time, a system where they have what's called resonance. So particularly the 4 Galilean moons are all in a certain resonance with each other. So, the closer moon to the Io, the closer moon into Jupiter, it goes around, for every 1 time around, every 4 times it goes around, the next one out goes around twice, and the next one goes around 4 times, and so forth. I'll probably mush that all up, but you get the idea.
Doesn't matter, yeah.
So they're in a resonance, which means it's very repeatable, and the moons, because you've got to remember that everything in a system interacts with each other. So all of our planets, all the planets in our system actually interact with the other planets, and their gravity, although tiny compared to the gravity of the sun at the centre, does have an impact on it. So what this means is in the early stages of the solar system, the planets were still figuring out, and that's to sort of anthropomorphise it. It's not like they were going, well, actually, you take the inner area and I'll go out there. It was all down to physics, and there was a bit of migration that went on in that process, and it seems that David, as you mentioned before, David from Research Institute in Boulder, Colorado, he has run this backwards and found that one very strong candidate for explaining how this kernel ended up where it was and ended up in the configuration it is that it was locked in some kind of resonance with Neptune as Neptune made its migration further out in the solar system. Now, the interesting thing is that everything works out until Neptune basically he's rolled it back about 4 billion years, and he found that these things have been swept up in Neptune's gravitational field as Neptune moved away from the sun. But then as Neptune moved to about 4.2 billion kilometres from the sun, suddenly it jumped outwards faster, and it meant that the kernel basically lost its tie to Neptune, and it continued off on the trajectory it was on, whereas Neptune had suddenly jumped, this giant, step outwards. The only thing to really explain that is that there was a gravitational interaction between Neptune and something else quite big. So basically, another gas or ice giant is the sort of thing that could have pulled it out. Now we know what's here now, that it's nothing that's in the neighbourhood now that could have done it, but it's very, very possible. And it's long been posited that there were other, gas or ice giants in the system, and that they had been ejected entirely from the system. And we do actually see this. We do see this with other systems where you've got, rogue planets effectively that are just been kicked out of their system and they're just floating on by
in interstellar space with no connection to any other star or
planets.
Absolutely.
And I've mentioned there's a an online website. I can't remember what it's called anymore, but I have mentioned on the show before that you can basically just play with different orbits, put objects in different positions and give them different spin rates, and the system will basically rotate them around, and you'll see what happens. And it's very, very common when you have what's called a three-body interaction that two of the bodies end up in a stable orbit. One of them gets thrown out of the system completely, and that's quite possibly what happened here.
Wow.
Well, how long ago were they positing that this happened?
So I'm not really clear, actually, to tell the truth.
So it was when Neptune and this kernel was about 4.2 billion kilometers from the sun. But yeah, it doesn't say what time frame that would have been.
Because I was just wondering, and maybe I'm probably totally off base here. Could you look in the neighborhood? I mean, because how fast would it be traveling, and could you possibly if this fifth planet was?
It seems to be long enough ago that you've got to remember this would have happened quite early in the very early stages. The system settling down. So Neptune was still on the move, and it was still moving outwards. And we know from Neptune's orbit it's a little bit odd anyway. So we know it has migrated for sure. If this was ejected, it's probably like 80% of the age of the system ago.
Okay,
so it would be quite far out. And because it wouldn't have been necessarily, gravitationally bound to our star at all anymore, it would have quite possibly ended up on a fairly straight trajectory. And we'd never find it. There's no way in hell. It's just too cold. There's no contrast with the background.
But we found other rogue planets before. I mean, we just sort of happened upon them.
They've been posited to exist.
I thought we'd actually found them. Okay,
we've had hints of things with some occultations. So we've seen dark things move in front of stars before. They're really the only way that we can possibly detect anything that's dark outside of our system.
Yeah, and even then, you don't necessarily know if it's a planet or a big cloud of dust that's rapidly moving or something.
Yeah, so clouds of dust are easier to discount because there would be we're talking like tiny increments here, but there'd be a dimming, not more or less a complete blackout and then complete. Yeah, okay. So dust is easier to discount, but what you don't know is how far away the object is between you and the thing that it passed in front of. So it could be something really, really big, really far away. It could be something a lot smaller, much closer, like, for example, like a comet or something like that. It's just really hard to tell without, some more data as exactly where the thing is. But, it's certainly very, very likely that there are rogue planets out there, and they're just really hard to find.
And a rogue planet like this one, if it was ejected from our solar system, it's got no gravitational interaction with our sun or any of the solar system bodies. There's no friction. There's nothing to slow it down. It's going at the same speed that it would have been when it was ejected, so it could be anywhere. Yeah.
True, and also, winds back our system, like our star's actual formation. Yeah. It initially would have formed in a stellar nursery with a whole lot of other stars, and we did a story not too long ago about another star that had been found that seemed very much to be a cousin or even a sibling to our star. So again, this may have been sufficiently far enough back that it was ejected into, the expanding stellar nursery of the star's siblings. It may have then been captured by another system. Who knows? But it's cool to think about.
Yeah, and it's probably something that we'll never really know.
No, we'll never know. But I mean, this is one of those things about. What attracts me to stories like that is just. I love that we can do this, that we can track things back with such accuracy, and it's really testable because you plug in the maths of things that you absolutely know for sure, and you wind them forward and back, and then match it up to observations of that period, and if they match exactly, then well, the maths is pretty sturdy. So we used exactly this type of mathematics to send probes out. New Horizons relied on exactly this to get where it did, because obviously when we launched it, it had to go and do a lap of Jupiter to get an orbital assist, gravitational assist, and then it was speeding out to a point that Pluto would be passing in the future, which is just cool.
Very cool. Well, let's come back to Earth and start talking about influenza. Now, we all know that the flu virus mutates remarkably quickly, which means each year there are different strains to deal with and thus new vaccines. But this week, 2 independent teams, and that's what I love about this, 2 separate teams working not together at all, reported in the journals Science and Nature Medicine that they've been tinkering with a piece of viral protein so that it can teach immune systems to fight whole groups of viruses rather than just a single strain. Shane, this is the first step towards creating a universal flu vaccine.
Yeah, definitely. And it's the holy grail of this sort of research, because the last thing you want to be doing really is developing a vaccine every year for a mutating virus. I mean, it's not guaranteed to work.
Come on, Shane, haven't you been listening to the anti-vaxxers? Drug companies make millions off these vaccines.
Don't make me hurt you.
And so do you, don't you, Shane, as a shill?
Oh, yeah, because I'm an effective shill. I really am. Dear God.
Sorry
anyway,
for that.
Where was I?
That you don't want to be making a new vaccine every year. You want to make one vaccine to cure them all.
Well, not necessarily to make a new vaccine, but like from an effectiveness point of view, it's risky because you never know what strain is going to actually. You can predict in this case which one might be the worst one, but you can never know for certain. I mean, and apparently last year's vaccine wasn't that effective. It only had about 23% effectiveness or something like that. So
that's last year's Northern Hemisphere vaccine, because in the Southern Hemisphere we have obviously our summers, the Northern Hemisphere's winters. We are basically guessing what the most common strain of the virus is going to be
based on what happened
for us, based on what happened in the Northern Hemisphere. Yeah.
And I mean, the problem with the flu vaccine. The reason the flu virus is such an effective pathogen is because it mutates so quickly. And I'll get into a bit of the virology of it here. The way it sort of the flu virus gets into your cells, it's got these little little molecules on its surface called hemagglutinin, and that's what it uses to gain entrance into the cells, and that's what keeps mutating every year, and that's one of the reasons it's so effective, is because it just changes all the time. So it's the way it manages to keep reinfecting and reinfecting. So our immune system will make antibodies against that hemagglutinin, and it will be quite effective in the short term, but it won't have any effect on next year's strain, or even possibly even next week's strain. What's interesting about hemagglutinin is that the head changes a lot, but the actual thing that keeps it upright. So think of it like, there's a really nice little analogy in one of these articles where it says, think of a planet covered with trees, and the head of the trees is kind of like the hemagglutinin head, and the trunks are the stems, and the stems are pretty much static. They don't change very much at all, which makes sense because they're kind of they're structural, so you don't want to have too much of a change in those genetic sequences, otherwise things could go haywire. The problem is that the good thing is that apparently our bodies will develop antibodies against these stems. The bad thing is that they don't necessarily. It's very hard to elicit an immune response against them if you include them in a vaccine, because apparently, due to the way the molecules work and are structured, if you put this in a vaccine, the head will be targeted, the stem will be ignored. If you put the stem in by itself, it tends to break up, so it's a bit hard. It's very, very hard to work with. So what these groups have done independently too, which is, and I'd really like to know what happened behind the scenes here. If they were in contact with each other, if they knew what the other group was doing, I'm sure they probably did, and if there was a race to publish, which I'm sure there probably was. But the important thing is that they've both managed to find a way to create vaccines in which they can include both the head and the stems, and include it in such a way that the stems are stable enough that they will elicit an immune response in animal models. So they've tested this against, I think, mice, rats, and ferrets, and it's been quite effective. So this is the next step into, basically, the next step is human trials, essentially. And yeah, hopefully that will happen. That will happen.
Yeah, no, that's really cool. I mean, I've always wondered, why is it that we can have one vaccine for polio, but obviously influenza, it just mutates so much faster that we can't eradicate one strain altogether before it's mutated into another one.
Yeah. I mean, what I struggle to understand is because the hemagglutinin part is the part is the most obvious. So you'd need to have penetration of the antibodies into past that hemagglutinin head into the stems and I don't know how that would work in vivo or in the animal model, but apparently it seems to. It's not as effective apparently in macaques, in monkeys. So it might just mean that they have to do a bit more research, develop a bit more, so.
But with this universal vaccine, apparently the process of getting to that stage now is a really inefficient process. Is that right?
It's not even inefficient. It's more just that it's very hard to, because there are different influenza strains too, and it isn't just the hemagglutinin either. It's also another subtype that's involved with that you've got to take into account. So yeah, it's not that it's inefficient. It's just very difficult, essentially.
Okay. Well, that's one to obviously follow, and we'll keep an eye on it, because it would be a huge and significant achievement if we can one day have one vaccine for flu that eradicates influenza.
But then our shield dollars will be gone, and that'll be terrible. It
would. But you got to remember, I mean, people do still die from flu.
Yeah. It's a serious disease, and it's people. I mean, and what annoys me the most is that people sort of use it very blithely. It's like, I've got a bit of flu. And it's like, no, you don't. If you had flu, you'd be really, really sick. You've got a cold or something like that. A flu actually knocks you right around and keeps you in bed for weeks. So,
well, with luck, this will even be able to combat the deadly man flu, which would be wonderful.
Oh, no, nothing about that.
My wife was suffering from man flu earlier.
Wait, what?
Last week. Yeah, it was the worst flu she's ever had. I said, it sounds like man flu. It's you come down with it. I feel so bad.
Well, let's move on then and talk about psychology and, more importantly, reproducibility. Having other people replicate your experiment and get the same results is one of the cornerstones of modern science, except it now seems in the realm of psychology. Professor Brian Nosek from the Department of Psychology at the University of Virginia has, over the last 3 years, managed to get a lot of psychologists around the world to repeat 100 published psych experiments in their own time. Like, their spare time. This is not paid for by grant funding or anything. They've got a few minutes left in the lab. Let's do a few psych experiments. Probably not in the lab anyway. And they've got some rather alarming results. Although of the 100 studies originally reported, 97% of them had statistically significant results. Once they were reproduced, only 36% of them were statistically significant. And they also looked beyond statistical significance. They looked at the effect sizes of the studies. So that measures the strength of the phenomenon. If you have an experiment that shows red lights make people angry, for example, the effect size tells you how much angrier they get. And again, the results were worrisome. On average, the effect sizes of the replications were about half of the originals. This is a fairly worrying indictment on the field of psychology, isn't it, Penny?
Well, look, yes and no. A point's been made that some of these results tend to be from really deep-seated psychological biases that all researchers have. It just happens that this study's been done in the field of psychology.
Sure.
There's a few explanations. Only results that are positive tend to get published. It's actually really legitimate and important science to say, well, I had this hypothesis, but it wasn't supported. No one wants to read that. No one wants to read, red lights don't make people as angry as they thought, or something. It's a bit blah. So people tend to look for data that is statistically significant before they go any deeper into their thing. So there's this sort of bias, and it means that it's not like you've declared, this is my hypothesis, I'm just going to test it. You kind of get all this data and then find something of significance from that data. So someone else who's doing your experiment might not necessarily find that from their data set. The other thing is that, and this is not meant to be an indictment, is that the original work may have been carried out more carefully by people more skilled in that particular area. I mean,
sure.
We don't know that the quality of the replication, as you said, no funding, no blah, blah, blah,
It's in your spare time, yeah. It's more rushed, perhaps.
It's interesting, and I think it would be very interesting to see this in other fields of science, because I'm genuinely not sure, like, apart from the really big controversial stuff, like remember that, what was it, the faster than light?
The neutrinos that went faster than light.
The neutrino thing, yeah.
Yeah.
How much stuff actually does get replicated in chemistry, say, or physics or biology?
Sure. I think you'll find the exact same things in other fields in terms of the publication bias, certainly.
Be mean to psychologists because, I mean, in a way, well, at least they're doing this. Someone has decided to do this study.
Yeah.
And have a think. But it is interesting, and I think it also, in some ways it makes me sad because you think, oh, well, it's just another play for anti-science people to go, oh, you see, it's not even true. And that's not really the point. I mean, the point is it's just another way in which we need to criticise things, and maybe the whole journal system is not working as well as it should be, but I don't think that that's necessarily a bad thing to realise. And I don't think that having realised that, maybe if the way that we publish is influencing the kind of results that are found.
It points to a number of faults or weaknesses, I guess, in the way modern science is done. And I think there are some steps towards correcting it, like open access journals are making a lot more data and a lot more research available to everyone and not just people who have access to the nature journals or Elsevier journals. But there's also, I think a study like this raises the awareness that there are certain criteria and ways of looking at science that you need to always bear in mind. You can't just read a journal article, look at the conclusion and go, well, this is what happened. You need to take it in context with all the other science that's been done on that topic. You need to view it with a more contextual eye, I guess, is one of the key points that I got out of this. So while we're talking psychology, Penny, let's talk about a recent and somewhat bizarre study. What strange and spooky things happen when you stare into someone's eyes for 10 whole minutes?
Which I don't think I've ever done.
10 minutes is a long time to be staring into someone's eyes.
Remember you have those staring contests when you were kids? Do you remember doing that?
Yeah, but never for 10 whole minutes.
Maybe a minute?
Yeah. That was freaky enough, though. I remember those. Anyway, sorry.
I thought this was interesting. And I mean, again, I guess just having talked about that other article about replicating results, I'm like, I wonder, as I do with a lot of things like this. But the idea is that if you when two people stared into each other's eyes for 10 minutes in a dimly lit room, they tended to end up in a mildly dissociative state, which is an altered state of consciousness. You've lost your normal connection with reality. And there were some really odd responses. Everyone said that the experience was compelling. People had hallucinations. Some people thought they'd seen a monster or that the face became deformed. Time seemed to pass in a different way to usual. People seemed to see the faces in the room in black and white. So this is kind of odd. And it apparently is much more stranger than looking at your own face in the mirror for 10 minutes. Because I was thinking, I wonder if I could just stare at myself for 10 minutes and see if that same thing happens. And apparently
you have two children. Where are you going to get 10 minutes to stare at yourself in the space?
At 10 minutes, I would not be staring at myself in the mirror.
If you did, you'd be staring into the mirror going, why?
And someone is bashing at the door going, Mummy, Mummy, Mummy. But I do find this really interesting. I studied archaeology at uni, and one of my friends was looking at Minoan, I think it was Minoan, anyway, like prayer rituals and this idea. And I did a little thing for her where with a group of people, we all stood in a darkened room and we mimicked the postures of certain statues. And it was a strange experience. And so it's interesting to think about, we normally associate altered states of consciousness with drug taking or, something really physical or pharmacological, I should say. But there are different behaviours that we can do that can lead to these altered states. And, it's interesting to think that just staring at someone, and 10 minutes is a long time to stare. But it's actually quite a short time, really. Like, if someone said, oh, look, you're going to see the universe and experience God, all you've got to do is this, I just find it really interesting how, I'm guessing things like hallucinating monsters and seeing in black and white are kind of side effects of some other process going on in the human mind, because we haven't really evolved to stare at each other's faces for 10 minutes, and yet it's the sort of thing we can find and investigate, and who knows what it really is telling us about how our minds work.
It reminds me a lot of just sort of mindfulness, that if you sit and contemplate sort of nothing for 10 minutes, you can get a altered relaxation or meditative state. And I wonder how much is just that combined with an imagination being prompted by a face, if that makes sense, and looking at someone's eyes.
Faces are very powerful, and a lot of our brains have evolved to, recognise. I think of all the Jesuses in toast and stuff. We're really good at recognising.
Like Jesus.
Well, more recently, there was the face of Donald Trump in some butter. Oh, God.
Yeah, that wouldn't give you nightmares enough.
But I think if you were to stare at anything for 10 minutes, you're going to start seeing things. Like if I'm lying in bed just staring at the ceiling and just thinking about something, you start to see the is it cells or something that you're seeing in your eye? I can't remember now.
Like those little floaty
things.
Yeah. You start to see little sort of specks of things, and then exactly as you're saying, Penny, we've got these pattern-making brains that want to join the dots on things and turn them into stuff. I could totally see how you'd start seeing faces, but I don't think it would be unique to staring into someone's eyes. I think it would be just looking at anything for that long, any one thing.
Yeah, I mean, when you think about it, how often do you sit there and concentrate on a specific object for more than about, say, a minute? Yeah.
I can't concentrate on anything for 10 minutes.
Yeah. Oh, apart from a TV show.
Even then, there's Twitter and there's a...
The control group was staring at a wall. So... But
that's the thing, that how controlled was the staring at a wall?
Yeah.
Were they staring at an area or were they staring at a point?
Yeah, true.
Big difference.
Look, I'm not... But it did make me laugh, and then it made me think.
Do you think it might be an Ig Nobel candidate? You're good on that, Penny. You always think of studies and put them in this could be an Ig Nobel candidate. I never think of that until the Ig Nobels are announced, and I go, oh yeah, we covered that, and it didn't occur to me that it was an Ig Nobel award. But I think that just about wraps up the show. So as usual, we'll have all the links on the web at scienceontop.com/199. You can leave a comment there. You can email us, feedback@scienceontop.com. You can drop us a message on Twitter and Facebook. Wonderful to have you back again, Penny. Thank you so much.
Oh, it's so nice to be back.
And thank you, of course, Lucas and Shane.
Yeah, no worries.
Thanks, Ed.
And thank you, everyone, for listening. We'll be back again next week, putting science on top of the agenda. Join us then.
She was making breakfast this weekend. Take a look.
All right, closer. Look a little closer. Jan Castellano says she saw it immediately in the brand new tub of butter. She sees Donald Trump's face staring right back up at her.
Donald has very distinctive facial expressions, of course, so she spotted his butter doppelganger immediately. Look at that.
The side-by-side's perfect.